Thank you very much, Tulin, for the introduction. And before I start, I would like to thank University of Arkansas, NSF, SIAM, and everyone who made this event possible, and in particular the local organizers. I mean, as much as it's in their control, I think everything is running smoothly. I'm actually very unhappy that we are still in the pandemic, because I'm pretty sure we will have more students here, and I think it's a great opportunity. As a student myself, I benefited the most with the smaller events when we have excellent speakers, which are actually among not thousands of people that you have to search for them, but they're around. So I think this series is a fantastic opportunity, and I'm very glad to be here. So I will talk about, I will continue actually and relate to what Yusuf was talking about, a lot of different techniques for eigenvalue computations, but also in a lot of applications that we are having, in particular in quantum chemistry. Yusuf mentioned about that, and other more challenging applications, that the problems also become much more complicated and much more challenging. And on the way, it's a joint work with several people, and you will see them on the go, but one of my collaborators is Yusuf Saad, and so he's here, so in case you'll see his name definitely popping up. Okay, so let me first talk about some motivation. We classically know a lot of eigenvalue problems that Yusuf mentioned from the classical fluid structure interactions and a lot of other applications. I'm going to talk about slightly different class of eigenvalue problems, in particular what we call the nonlinear eigenvalue problem. And I have to also go back to Sarah's talk. Actually, when we talk about nonlinear eigenvalue problem, we have to be a little bit more precise. So we have actually two classes of nonlinear eigenvalue problems. I will concentrate on the class that, given the matrix value function, basically the T of lambda, so it's nonlinear eigenvalue problem in the eigenvalue, not in the eigenvector. So we have the matrix valued function, which maps from a certain domain D, which is usually a subspace of the complex plane. And we are searching for non-zero vectors X and Y such that the following condition holds. So this is a general form of the nonlinear eigenvalue problem. And you can think about it, if your T of lambda has a form A minus lambda identity, then this problem basically boils down to the classical linear eigenvalue problem. And the problems of this type arise in a lot of modern applications, in particular in the modeling of photonic crystals. So photonic crystals are, you can think about them as a semiconductors of light, where we are trying to block certain waves from propagating, and they occur very broadly in nature. So if you look on the butterfly wings, you have this very particular structure, and the fact that we see certain colors and we don't see other colors is due to this photonic crystal structures. But we would like to actually be able to fabricate materials which have those properties. The other thing is nanoelectronics, of course, in designs of chips. We also want to propagate certain wavelengths, and that brings us also to the nonlinear eigenvalue problems. And for example, when we consider particle accelerator cavity, so if you have particle physicists building detectors and they have, so this is, for example, Fermilab is working a lot on building this particle accelerator cavities. They use also one of the mathematical problems which arise is actually the nonlinear eigenvalue problem. So this is our object of interest for today. And for those of you who have not been, who are not familiar, I'll just give you a brief introduction of how the linear and nonlinear eigenvalue problems are different in nature. and actually how their characteristics led us to very different type of methods. So we have a general, we have a general statement of the problem. So this is the nonlinear eigenvalue problem. T can be any function of lambda. So as I showed you, very simple T of lambda, we can establish the linear eigenvalue problem. It can be any polynomial of lambda. It can be rational or exponential function or any other exotic matrix value function of your choice. In the following, for the simplicity and also for the purpose of having some theoretical foundations, we'll assume here that it's a holomorphic functions. And as I said, the linear eigenvalue problem is just a very particular case of the nonlinear eigenvalue problem. So if you think about the classification, linear eigenvalue standard, so if you take T of lambda, we get the standard eigenvalue problem or generalized eigenvalue problem, which we have when we have a second matrix instead of identity. And we know from theory that if the matrix A and B are of size n, then we have at most n eigenvalues as a solution of the eigenvalue problem. Some of you may have seen quadratic eigenvalue problem, for example, mass spring damping, the classical example. And then we know that if we have the coefficient matrices of the size of n, we actually can show that this problem is equivalent to the linear, what we call linearization. So linear eigenvalue problem of double the size. And then we have 2n of eigenvalues. So then we can go to general polynomial case. And so we have powers of form I equal to 0 to d, and then depending how many of those coefficient matrices we have, if all of them are of size n, that we know we have d times n eigenvalues. But if you go what we call the general nonlinear case, so we have some function of a lambda, fi of lambda can be arbitrary function, then we are in the case that even that the coefficients of this problem are matrices of size by n, we can have infinitely many eigenvalues. And that's causing us a lot of difficulties in terms of even calculating and further difficulty for the actual analysis of those type of problems. Okay, so some of the characteristics. So we have the main problem when we very often have is that we learn about like linear eigenvalue problems and we have some expectations, we have some characteristic, and then we move to nonlinear eigenvalue problems and we expect, oh, so we try to generalize. And very often, unfortunately, things which we know from linear case don't generalize to the nonlinear case. So similar as for the linear eigenvalue problems, the eigenvalues of the problem are the solutions of this equation. We take the determinant of T of z, which is a matrix valued function, and we calculate so we determine all the values z for which this is equal to 0, and this is how we get the eigenvalues. But we also know that past the size of 2 by 3, 2 or 3 by 3, calculating the eigenvalues through the determinant is not really the way to go. Other thing, even if T is irregular, so it's not, if we take that determinant of T z is not equal 0, in the sense it's not explicitly 0, we may have infinitely many eigenvalues. And that's the case that I have shown you for general nonlinear eigenvalue problem. The other thing, which is the most problematic things in practical applications and in calculations, is that the eigenvectors associate with the distinct eigenvalue. First thing we learn in linear algebra, we have a distinct eigenvalue. Then we know that we have a set of linearly independent eigenvectors. Well, we don't have it here. So we may have distinct eigenvalues, but they don't have to be, their corresponding eigenvectors don't have to be linearly independent. And I will show you a very simple example of that in a second. So the algebraic multiplicity, other very important concept from eigenvalue problems of an isolated eigenvalue. Although it is finite, it's not anymore bounded by the problem size. Since we have infinitely many eigenvalues, the algebraic multiplicity can actually be larger than n, so the size of the coefficient matrix. So if some of you are interested in those type of problems, we are lucky enough that we have pretty well covered literature reviews. So as early as 2001 and then 2004, we have a lot was written about quadratic eigenvalue problems. Then in 2015, we have a very good review paper. All those are actually review papers with lots of resources on polynomial eigenvalue problems. And then on nonlinear eigenvalue problems, we have the paper by Heinrich Voss from 2014. That's in the linear algebra handbook, a whole chapter, review chapter about nonlinear eigenvalue problems. And the recent one by Stefan Gütel and Françoise Tisset in 2017, looking on a lot of this, what we actually know up to date for these problems. Okay, so now I will give you the example that I mentioned, that we have an issue with the fact that even if we have a distinct eigenvalue, we don't have necessary corresponding eigenvectors being linearly independent. Take this very simple matrix value function. And the eigenvalues of the T are, of course, the roots of this characteristic polynomial. So we know they have this form. So there are infinitely many of them, as I said. So this plot is just restricted fold. We have 42 out of infinitely many, because they're going with k as far as you want, eigenvalues of T. Lambda 0 equal to 0. So as a 0 eigenvalue has algebraic multiplicity 2. And all other eigenvalues are of algebraic multiplicity 1. However, the vector 1 minus 1 is the right and left eigenvector for all eigenvalues of lambda. So of course, we have distinct, you can think about distinct eigenvalues, but they all share this vector as an eigenvector. And we know that the fact of having linear independent eigenvectors is important from the computational point of view. So we know that here we already start with a very different setup. Okay, so again, when we are talking about modern applications, I want to also talk about the difficulties, not only that the problem is a nonlinear problem, but also we are talking about really huge problems. So sometimes, so one of the applications is an electronic structure, and it in quantum chemistry, and this was mentioned in several talks as one of the really challenging applications. So in ideal world, what quantum chemists are interested in is they are interested in many-body Schrödinger equation, which we see here, which is actually when you think about it's a high-dimensional but linear problem. But the dimension is so high that we actually cannot solve this problem efficiently. So then we try to find a better model which we can use such that it can be tackled in practice. And that brings us to one of the other equations, which is the Kohn-Sham equation, which is also an eigenvalue problem, which can be treated as a model problem, because we don't have, it's still large, but it's still tackable. But we move from the linear to actually the nonlinear problem. And here the nonlinearity actually comes in the eigenvector. But it's a similar class of problems when we have to deal with very different computational methods. And we know, okay, as long as we are interested in kind of extreme eigenvalues, the smallest or the largest, we have some very efficient methods that Yusuf was talking about. But here we also not only have the gigantic problem, but in order to actually have a meaningful solution in practice, we want to get maybe 10% of the eigenvalues calculated. And in this if this 10%, even if it's 10% of the smallest, or starting from the smallest or the largest, eventually we end up with the fact that we actually have to compute the interior eigenvalues. So one of the techniques that Yusuf was just mentioning is about how we do the divide and conquer, and we can use polynomial filtering and different techniques to actually calculate eigenvalues in pieces. So if you have a spectrum, which is like, this is your 10% of bands, well, maybe we can do it in slices. So there is this slicing technique. It's like a divide and conquer approach. So you divide your interval, it's here, into pieces, and then you calculate your eigenvalues in pieces. However, if you have a large spread of the eigenvalues, so let's say that these are eigenvalues close to 0, but you have some which are very large, using a polynomial filter is not very efficient, because you will have to have a filter which kind of covers this large spread, a polynomial, which means you will end up with a very high polynomial degree. And evaluating polynomials of high degrees is not really computationally efficient, and it's not something we can do in practice. And moreover, if your problem is even a generalized eigenvalue problem, we cannot do it even with polynomial filtering. So there is a large class of what's called rational filters to deal with, and I'm still talking in the context of linear eigenvalue problems, as an alternative. So instead of using polynomial, we use the rational functions who are giving us a better behavior if we have a spectrum of this form, such that we can build a rational function which will be able to approximate, kind of represent this spectrum, and then incorporate these rational filters in methods like Lanczos or Arnoldi for calculating the eigenvalues. And these rational filters actually exploit the tool that we will use here a lot today, is the Cauchy integral representation of the spectral projector. So that's what I'm going to talk next. So let's just briefly review the Cauchy integrals and the contour integration. So the one of the very powerful theorems, which I guess we learn in complex analysis, or maybe in some other courses, is the Cauchy theorem, or Cauchy-Courset theorem sometimes. So if we have an analytic function of the simple connected open region of the complex plane, and if we have a contour in this which encloses our region D, then if you take a contour integral of this function over the contour, it's equal to 0. So that's the most common statement of the Cauchy theorem. And then we have what we call the Cauchy integral formula. We have, again, an analytic function on a simple connected open region. Then we know that if we take the contour integral of this rational function and with the scaling function, if we take this contour integral is equal to the value of the function at point A, if A is inside the contour, and it has a value 0 if it lies outside of the contour. So basically, you can think about it. Okay, I built an object such that it will tell me if something is inside or outside of the contour in the complex plane. Okay, and then we have another useful variant, a Cauchy argument principle. So if you have a meromorphic function, say the similar assumptions as before, if we look on this contour integral, so we have the derivative of z divided by f of z, we calculate this quantity, then we know that this will correspond to the numbers of zeros of function f minus the number of poles that the function has. So we can illustrate it. And it has been used in practice in a lot of applications before. And we'll see how we can use it to solve an eigenvalue problem. So one of the very important object for today is representing a matrix valued matrix function f of a. So a is a matrix using the Cauchy integral. And I believe that if someone is more interested, you can learn in HIAM 2008, where the famous book on matrix functions. So if f is a function, but now we are evaluating it on the matrix. So what we know, we learn it in linear algebra. Okay, if A is diagonalizable, we can just evaluate f on the set of eigenvalues and so on. But if we have f of A in general, this matrix value function can be represented by this quantity, which is a contour integral of the inverse of the resolvent times the value of function z. So this definition of the matrix function f of A establishes a very powerful tool, which we call the Cauchy integral formula for the matrices. And this will be the main tool we will be using when we want to calculate eigenvalues for nonlinear eigenvalue problems. Okay, so what is the connection between the Cauchy integral, so this matrix valued representation, and the solving eigenvalue problems? Okay, so one thing which is very powerful already using this argument, Cauchy's argument principle, is actually, if you think about your function to be the determinant of zi minus I, if you use the Cauchy argument principle, which I showed before, it actually tells you that you can determine the number, if you can evaluate the contour integral exactly, you can get, using this principle and using this particular function, you can get exactly the number of eigenvalues in the region enclosed by the contour. So imagine you have a set of eigenvalues, you just put a contour around some of them, and if you have ability to evaluate this contour integral exactly, you will be able to say how many eigenvalues exact you have in this region. Okay, and this has been studied in very different contexts. So just give you a little bit of overview if you are interested in exploring it more. Study of inclusion regions for matrix eigenvalues. It started back to Brunaldi in '94. There was a line of work in this direction. Over the years, people are studying what are the inclusion regions of the matrix eigenvalues. So the simplest one, which of course we know, is the Gorge-Goring type result, but that's of course under the assumption that we have diagonalizable matrices. So these results are kind of going a lot beyond. Exactly, another thing, counting eigenvalues, and then you will see some of the approaches which we are using, and also and Yusef's work on quantum chemistry, in order to use those methods, even if you want to determine the size of the subspace that you have to use in your subspace iteration method, you need a good estimate of the number of the eigenvalues. We have also stochastic estimation methods for large eigenvalue density problems. So the density of eigenvalues is used in estimating the density is used in many practical applications. So a lot of papers in this direction, and then approximable spectral densities. Also, you also see the Yusef's work here in the context of quantum chemistry and a lot of other applications. Okay, so let us see why Cauchy integral theorem for matrices makes sense to use it as a tool when we want to calculate internal eigenvalues. So suppose your matrix is diagonalizable, and this is the kind of the illustration. Of course, most of the problems which we are handling may not be diagonalizable in practice. In the quantum chemistry, very often they are, so we are lucky. But we have an eigenvalue, so eigenvalue the composition of the matrix A, and we know that we can write it basically as a sum of rank 1 matrices using the spectral decomposition. Okay, now let's just look on this function f, analytic and the inside of the contour C, and the contour is enclosing the spectrum of A. So I evaluate f of A using the Cauchy integral interpretation, but now I know that matrix A is diagonalizable. So of course I can use the eigenvalue decomposition. And then if I look on this object, and I can take some things that of course don't depend on the z out, which boils down to, okay, we have here the classical formulation, which we know what happens when you evaluate the function of the matrix. So we get the eigenvector matrices, and then we have a function of arbitrary function of the eigenvalues. Okay, so we still have a representation in terms of rank 1 matrices, but now instead of just eigenvalues here, we have this function f evaluated of the eigenvalue. Okay, so now let us suppose now that f of z is a very specific function. It's an indicator function such that if f of z is equal to 1, that means that z is inside the contour, and it's 0 outside on the region, which is actually not contained in this, if z is not in the complete spectral array and this domain that we are interested in. And let's say that the contour is exactly the boundary of our subset of interest T. Okay, so if we do this calculation again, what we realize, and this is a typo, sorry, that was supposed to be instead of this star, is that if lambda I is in this set D, then f of lambda is equal to 1, otherwise it's equal to 0. So for every lambda I in the set D, we actually have this representation. And if you look what this sum is, it's exactly a spectral projector. It's exactly a spectral projector associated, so spectral projector onto the invariant space, subspace associated with all the eigenvalues lambda I and D. So if we can do it exactly, okay, I'm getting this a spectral projector, and we know if I have a spectral projector, I can just use it to determine all the eigenvalues and eigenvectors. So it's kind of reverse engineer. If I have a spectral projector, why do I to get a spectral projector, I need the eigenvalue decomposition, and I use it for calculate eigenvalues. But that's just a kind of theoretical motivation how the connection comes in. Okay, so we have shown that the spectral projector associated with the eigenvalues of the matrix A, which are in some particular region of the complex plane, is exactly a contour. It's a contour integral of the resolvent with some scaling factor. Okay, let's just assume that we are interested in eigenvalues located in that we have a Hermitian problem. So all the eigenvalues are real, and we scale the region such that we are in the interval -1, 1. Then C can be taken just as a circle. So we take a circle which is centered at the origin, and then it has a radius of 1, and we are sure that the whole interval is then inside it. Okay, so we know we cannot do basic numerical analysis course. You know, we know we cannot calculate integrals accurately. So what is the way of calculating the integrals numerically? We use the quadrature rules. So if we use any quadrature rules to calculate numerically the value of this integral, we will be basically, if we have infinitely many quadrature points, we will get pretty good estimation. So we have quadrature node sigma I, we have some quadrature weight. If we build this object, the more quadrature nodes we use, the closer to evaluating the contour integral exactly, and the closer we are to the exact spectral projector. Okay, so we have integration nodes, and we have the corresponding weights, but we know that we cannot do it exactly. So we will call this object, depending how many quadrature nodes we pick, rho of A. Okay, so how can we use this connection to develop something which is computational feasible and effective, and use it to build an eigenvalue solver? And that brings us to the first part of the work we did on the nonlinear eigenvalue problem, the nonlinear Feast algorithm. So this was a work of Brandon Galvin, who was a graduate student at Amras, and now he's, I think, in LinkedIn, and Eric Polizzi, the original author of the Feast algorithm for linear eigenvalue problems. So how does the Feast method works in the context of linear eigenvalue problem? Okay, we want to compute the certain number of eigenvalues of this problem, a linear problem. We pick the parameter M0. So we define the M0 dimensional subspace, usually at random. So we are doing a subspace iteration method, but except of the fact that we are picking our subspace initially, we also applied to the set of vectors which we chose at the beginning, this spectral projector. So we know that by applying the spectral projector or its approximation at this point, we are bringing all the vectors into hopefully invariant subspace associated with the eigenvalues of interest. Okay, so let's say we have pretty good approximation of the invariant subspace. And if we have that, we can use the classical Rayleigh-Ritz procedure. So we project our original eigenvalue to a smaller dimensional subspace. And in general, if range of Q is a good approximation, we can refine the subspace as long as we get the convergence. We calculate the eigenvalues and eigenvectors of this projected problem. And since M0 is larger than a number of eigenvalues of interest, we can always get the approximate values for our eigenvalues of interest. Okay, this is how the Feast algorithms looks in practice. Of course, we don't have this spectral projector here exactly. And that's where the rho of A comes. So we have an approximation of the spectral projector determined using the quadrature rule that we picked for approximating the contour integral. So what is actually Feast? You can think about it's combining subspace iteration method with a filter or a contour integration technique, which is used, which is approximating the spectral projector. So you can call it accelerated subspace iteration, where the acceleration comes from applying this rational matrix function, because that's actually what it is. It's a rational filter in a sense. It's a projection method into the subspace of a fixed dimension. So we don't have a growing subspace as in a lot of other methods that have been using the contour integral approach. It's similar to the inverse subspace iteration. So if you have a inverse subspace iteration method, you just use one shift. So you get the approximation for one eigenvalue close to that shift, and then you can refine the shift. But now imagine you have ability to use multiple shifts at one iteration step. So this allows you to actually build approximations to several eigenvalues in your of interest. So you don't do it one by one. Other characteristics, subspace Q is computed in this way. Actually, if you use it's just you have to solve a lot of this. Well, actually not a lot. You solve as many as linear system of shifted linear systems as the number of quadrature nodes, and usually we are able to deal with a small number of quadrature nodes. Sometimes we also can use the same node with higher multiplicity. That's one of the work that Yusuf and Owen-Zix worked on. But all these systems can be solved in parallel. You don't have to solve in a sequential way because all these shifts are independent. There is no crossing information. So it's highly parallelizable technique. Okay, so it's not that this method is the only contour integral eigenvalue solver. In the linear eigenvalue problems, there are different types of methods. So it's a moment-based approaches by Sakurai and Sugura. They are using also the connection to the contour integral. There are also domain decomposition methods and accelerated eigensolver coming from the group of Yusuf Saf and Sad and other kind of different ways of doing rational filtering combined with, for example, Lanczos or any other kind of subspace method. However, in the context of nonlinear eigenvalue problems, there are also different approaches using contour integral methods. So there is one of the earliest methods is the Bayes method, which is using also the contour integral and estimating the moments. The concept is a little bit different. I will talk about that briefly. You have to build a Hankel matrices associated with the moments of which are coming from approximations of the different contour integrals, and then solve the generalized eigenvalue problem associated with that. So a very different approach. There is also Sakurai-Sugiura type of projection methods. There are other class of methods, which I will talk about briefly, how to build kind of linearizations using rational approximation, but I will start with the nonlinear phase. So if we think about, it's a nonlinear problem. So the first thing we learn when we have a nonlinear problem is use Newton's method. Okay, so let us look on our original problem. We have a nonlinear eigenvalue problem of the type that we have seen before. So we can think about it. If I add some normalization factors, I would say, okay, let's enforce the normalization on the right eigenvector. Then I can actually formulate my nonlinear eigenvalue problem as a nonlinear problem f of, now I have this vector. So I put the eigenvector on the top and the corresponding eigenvalue on the bottom. This is my new object. So f of this is equal to 0, where my f is looking this way. So this is my original matrix value function. This is just the normalization. Okay, and I want to, so if I have f of v equal to 0, I can use the Newton method on the f. So that's what is happening. And if I write Newton method directly for this formulation, this is what I'm going to do to get, which is actually equivalent. You can think about it. It's a nonlinear version of inverse iteration method. So you do the inverse iteration in a sense for the nonlinear problem. Okay, but we see already a couple of problems here. First, we have the derivative of our matrix valued function, and not only we have a derivative, but even if we have t, in each step, this t is evaluated and the derivatives are evaluated on different points. So we have to evaluate t, we have to evaluate the derivative of t, and then we can proceed with our iteration scheme. Okay, so the nonlinear inverse iteration was proposed originally in 1950 by Unger, and then Ruhe in 1973 wrote also a very interesting paper about solving nonlinear problems using the nonlinear inverse iteration, and that's how the formulation looked like. So very similar as we see the inverse iteration, right? We have this t, the derivative, then we do something to get an approximation of the next eigenvalue, and then we have the we use the vector we normalize to get the next vector approximation. But again, we have to evaluate t, we have to evaluate the derivative, not very practical. So then in 1985, Neumayer proposed what's called the residual inverse iteration, which has two main steps. So first we are given two vectors. So we have an approximation of the kth eigenvector and some vector wk, which is given. And there is a whole discussion about what this vector should be. You can even think about the left eigenvector for the normalization part, so for the orthogonality purposes. And then we compute the next approximation to the new approximation of the eigenvalue as a solution of the following problem. So we solve for lambda this problem. So if you solve this problem, that will define our new approximation of the eigenvalue. And then we have we do the two things. So now I have the new approximation, so I can evaluate t. And then in order to avoid calculating the derivative, updating it constantly with the new approximation of the eigenvalue, I fix the sigma, what we call a shift, and then I only have to evaluate t on the sigma, so that I can prefactor this before you do LU factorization and use it when I'm solving a linear system. And I also replace the derivative by a finite difference. So this, if you put that all together, this is the update you get. So we have xk plus 1, it's xk plus this update. So this is matrix vector multiplication, but then you have to solve a linear system. But since this sigma is not changing, so you can prefactor and use it in your calculation. Okay, but still this is one of the effective methods, but how to use this method now to calculate in interior eigenvalues in particular is that we have this one shift. So you can say this is kind of a generalization of inverse iteration for the nonlinear problem, but we still we have only one shift. And this also connects to the one of big machinery, and one of the theorem that makes the next steps possible is what the result of Keldysh in 1951, which tells us that if you actually take the inverse of this matrix valued function, and you have the fact that you have the set of eigenvectors, left and right eigenvectors, the corresponding eigenvalues, and so on, you can write this inverse of the matrix valued function using this decomposition. And then you have the remaining term, which is analytic in D. So if you take the contour integral of this expression, then basically you can get rid of this. So this is a very technical result, but actually this is a core result to use and why we can do in practice what we are going to do. Okay, so if we talk about contour integration for nonlinear eigenvalue problems, as I mentioned, there are different methods, nonlinear variants of Sakurai-Segura. So that's basically first results was only for the analytic matrix function. It's but there was a problem with accuracy, which was fixed later on. So that was one of the earliest method, also using contour integrals. Then the method of Bine, which was highly accurate, but it was using only the third and first order moments matrices to reduce the problem to the smaller dimension. But since it's used the Keldysh theorem, which is actually related to the Jordan canonical form, it was it's highly sensitive to perturbation. So there were some problems with those apparatus. So that's why we are still looking for the method, although I'm not sure if we're getting anywhere close to the method for solving nonlinear eigenvalue problems. Okay, so SSS is a projection type method. So as I said, we have a growing subspaces, and it's not clear how many of this, what it's called the moments of the Cauchy integral. So this K, how large we have to go. So Bain's method used K zeroth moments and K equals to 1. So first and zeroth and first moments here. Sakurai-Segura is you have to use as many moments as necessary, which is not clear. We cannot. It's very hard to estimate this number in advance. So standard fees uses only 0 moment, but it does not work in the case of the nonlinear T of lambda. So if we would like to use standard phase to just modify everything, let's take now to the T of lambda and put the 0th moment, this straightforward approach will not work. So that's why we proposed the nonlinear fees, which basically is that since we know that the linear fees was a generalization on the inverse iteration where we apply a lot of shifts at the same time, we thought, okay, then the nonlinear fees should be a generalization of the nonlinear inverse iteration where we can apply multiple shifts at the same time. So we were expecting first that, okay, let's do a natural representation, and that's how our approach should look like in terms of contour integral. But then we realized that if we fix the z here, using a constant shift, which is not equal to the approximation of the previous Kate eigenvalue, results in the fact that if we run this classical feast approach, we will get converged to all the eigenvalues of the matrix T of Z, but because since you fix Z, what T of Z is a matrix, so you'll find all the eigenvalues of this matrix, and that's definitely not what we are interested. We are interested in finding all the eigenvalues of the nonlinear eigenvalue problem. So we had to figure out how to properly state this contour integral subspace method to be able to do that, and that brought us to more refined statement of the inverse iteration, in particular residual inverse iteration method. So we decided that we should use the residual inverse iteration as and try to generalize it such that we can apply multiple shifts at the same time. And this allowed us to formulate this contour integrals method. So this is now kind of, you can think about that this will be our filtering function, which will make sure that we actually filter all the eigenvalues of the nonlinear eigenvalue problem, which are contained in the inside of the contour. And the good thing about that is if we make a choice T of lambda A minus lambda I, so if we go back to the linear eigenvalue problem, we will recover fully the linear feast. So that was an indication that it has to be a generalization in that sense. So the nonlinear feast is a generalization of the residual inverse iteration using multiple shifts. Okay, so this is how the detailed procedure looks. Again, we have the subspace that we pick, and we refine the subspace using the approximation of the contour integral. And again, here we have the residual vectors, and we have to solve some linear systems on the way. So the building blocks are exactly the same. And we combine residual inverse iteration with contour integral. We have accelerated projection method. We can solve all the linear systems independently using whatever method you want. We have a small nonlinear eigenvalue problem because we project the large one to the small one. So we still have to solve very small nonlinear eigenvalue problem, and it's highly parallelizable inherently from the feast algorithm. We have the theory. We have a little bit about the convergence. So we can do a convergence analysis in terms of, we can actually write this problem as a fixed point equivalent problem. So we know that if we have an equivalence, which we can show that if a point is a fixed point of this iteration, it has to be in the corresponding eigenvalue and eigenvector of the underlying nonlinear eigenvalue problem and vice versa. And we also have the characterization of the corresponding eigenvector. But without further going into details, on theory, I would like to show you some examples. So this is one of the examples from, so there is a very nice book about resonances by Zworsky. So that's one of the problems, scattering resonances on 1D. So we have it's scattering resonances in one dimension. We have some modeling potential. And this is the problem that we can actually write in terms of having the underlying PDE formulation. And then we can discretize it using a very particular discretization, finite element of particular on the particular domain. And this brings us to the following nonlinear eigenvalue problem, where the coefficient matrices are just coming from the finite element discretization, and we see also the potential. This is the spectrum. So if you take this problem, build a for linearization and calculate a long time to do the computation. So this is 302 scattering resonances for the potential equals to 10 using the full linearization. So we build the corresponding linear eigenvalue problem to just calculate all the eigenvalues. This is how the spectrum of this problem looks like. But what we were interested in is, okay, let's try to find some eigenvalues in very particular regions. So we took the circle and we as our contour, and we want to determine all the eigenvalues inside. So we have, so there are 22 complex scattering resonances lying inside the circle, which is centered at 0. and it has radius r 15.5. So this is a circle. It's not an ellipse, just the scaling. And the nonlinear phase was able to compute all the scattering resonances in 4 iterations using 16. So 16 total because we have 8 and because of the symmetry. Integration nodes on the subspace of size 30 using 4 iterations up to 10 to the minus 10 accuracy. The other problem, classical model problem, Hadler problem, which you see is fully nonlinear. This is this f of lambda, so it's exponential lambda minus 1. So it's not polynomial eigenvalue problem. Again, we can discretize. This is the spectrum. This is the spectrum of this eigenvalue problem. So you see that it's a lot of clustering here around, and we picked some region really in that clustered region here, and we said, okay, we want certain number of eigenvalues. These are the eigenvalue approximation. And you can see also how different, depending on the number of quadrature nodes, what is the accuracy and how many iterations you need. And we know the larger number of quadrature nodes, more accurate is your spectral projector or something which is associated. We don't have a full definition of the spectral projector. We could, in the nonlinear eigenvalue problem, let's call it a filter. So we get much more accurate result in this is the number of iteration of the subspace iteration. And the same, depending on the size of your space, if you have the larger subspace, of course, you have more vectors to, more directions to search, but you also have to, of course, so the accuracy is larger, but you also, each iteration is more expensive. So that's one thing, because we have to solve more linear systems. We did also the other line of work. I was stressed yesterday that everyone had so many, and I added some slides, and now I am ending at like that there is way more than I can handle. But in terms of solving this really difficult problems, Yusuf, myself, and our Yusuf's former postdoc, he was now a faculty in Morocco. Mohammed, we worked on the rational approximation for method for nonlinear eigenvalue problems, and the goal here was that, as I mentioned, in general, nonlinear eigenvalue problem can have this form, and you have all those coefficients being functions of lambda, and they can be as exotic as they want. The idea is, can we actually build kind of a different type of linearizations associated with those more general problem? So we say, okay, since we have those coefficients being the functions of matrices, why we don't use the idea of Cauchy integral to actually approximate these functions using contour integral? So using the Cauchy integral theorem, we say, okay, fj of lambda, we should be able to approximate it by some rational function of this point. And of course, if we select a set of contour integrals that is going to capture quite accurately each of these coefficients, or we can hope maybe to be able to build some nice representation, or what we call a different type rational inspired linearization. So what happens if you do that? Well, if you use the Cauchy integral as a way of approximating each of the coefficients in your nonlinear eigenvalue problem, you end up with a problem which looks like this. So this is kind of like a linearization in a very different fashion. So you have your quadrature nodes. Basically, in this, you have this kind of diagonal matrix. You have your coefficient b. So these are the one coming from the original coefficients of your nonlinear eigenvalue problem, and you can write this problem in that form. And then, if you see, this problem has actually very nice structure. So can we explore a structure? Well, we can. We can formulate this as a generalized eigenvalue problem. So of course, the dimension will of the linearization is going to be large, but we are not going to form this linearization. We are going to use the nice structure that comes from this linearization to reduce the computations. So it turns out that each of the problem, the whole linearization has this nice form. So diagonal and those two off diagonal blocks and the last block B0. So we all, in order to solve the generalized eigenvalue problem, we have to be able to solve linear system of this form. But we know how to solve this kind of linear systems from in practice. We can formulate the LU factorization of this shifted matrix and use the Schur complement and kind of rewrite this problem. And if we rewrite this problem, we actually end up with kind of two-stage procedure. So we have iterates over xk plus 1 and over vk plus 1. And what it ends up in is that if we use also some projection ideas, Rayleigh-Ritz projection in between, we end up with a very small problem. And we actually end up of solving those linear system, which reducing it to not the full size n of the linearization, but we can do it one column at a time. We only have to keep of one vector of length nc plus 1 times n. So the storage and using the fact that we have a lot of structure in that problem allows us to make this approach very computational efficient. So we not only project, but use the structure. So we never formally establish a large problem. We always work with those short vectors. So very interesting procedure. And then we tested that on the similar class of problems. So first, what we have to do, we have to approximate those coefficients. So if you look on the Hadler problem, we had these two coefficient functions. One is e to the lambda minus 1, one is lambda squared. So first we have to find what is the number of quadrature nodes for both of those functions such that we will get enough accuracy. And it turns out that if we pick 32 for both of them, we'll get approximation of these functions up to 10 minus 12. So this is, we pick this number of quadrature nodes. And then we use the shift and invert Arnoldi approach, but using this projection trick. So if we do that, we start with 40 random vectors, apply 10 steps of shift inverse iteration. Of course, we determine the proper space to perform Rayleigh-Ritz projection. And then we solve the reduced eigenvalue problem of this small size instead of gigantic linearization. And we compare it with AAA algorithm, which is one of the other state-of-the-art approaches for rational eigenvalue problems and likes. And this is how our algorithm looks like. We have to also take into account that it's not really a fair comparison because the 7 and 38 nodes are needed to approximate T of lambda up to 10 to 1 for the both methods. So we have to pay a little bit more in order to get NLIX, and they are also using adaptive shifts. So they are actually adapting the choice of shifts in their approach using the contour integral. So there's much more sophisticated heuristics inside those methods. And this is how we compare to that. And we did a one big, it was running for, I think, several days. So we took so we were given a pump casing model. So it's a finite element model with 1.8 million of degrees of freedom. So it's coming from the three-dimensional Helmholtz problem. And we were interested in approximating some of the eigenfrequencies that the engineers are interested in practice. So we did this calculation, and we were able to successfully determine the eigenfrequencies, and actually we were able to speed it up using some hierarchical matrices and some other, because actually our calculations were not the problem. The problem were that the center parameters and things like this in order to form the matrices, because the problem was so large, and actually cost a lot of calculations. Okay, so these are the details on this problem. So actually we had the initial subspace also for this 24 trapezoidal quadrature nodes. We had to assemble matrices using H matrix compressed versions for this coefficient matrices, because itself the problem is so large that even this coefficient matrices were large. And we use reduced subspace iteration to solve the same problem with 10,000 triangles in initial subspace size 40. And we have exploited the parallelism and everything. So we're very happy to get these results in much better accuracy and also relatively fast using this approach. Okay, and that I stop here because I'm already over time. Okay, thank you very much.
Any questions? I'm sorry if I missed this or just bring it. Wonderful. I'll ask you now. Okay.
I will repeat the question.
So the question is about the quadrature nodes. You have to choose them ahead of time. The number of nodes that you use. Is it possible to adapt the quadrature?
Okay, so the question is when we have the this nonlinear feast, there was discussion, okay, how do we choose the quadrature nodes? And at the moment we are choosing them fixed. So we choose, let's say 24, but yes, we can integrate approaches like the AAA algorithm use exactly that. It uses adaptive way that you can, depending how you're converging, you can change your quadrature nodes. We can do that. We didn't do that, but yes, there is no problem in doing this. So we can apply a lot of this common heuristics also in those approaches.
So let's check the chance. Oh, yeah, this is.
I think that was from the previous one. Yeah.
Just a comment, if you needed more hours, we could give hours
No,
to another lecture, not to make you
Thank you.
stress out.
No. My problem is I can have 5 slides and still talk 3 hours. So that's I think it's good to have the limit. Okay, so if anyone, so yeah, thank you very much. I have just one brief comment for the students. Please use this opportunity that you have so many excellent people and speakers here. Don't be afraid, we are not biting. Talk to us, because that may be your lifetime opportunity. I learned it myself. If you have lifetime opportunity, don't waste it. You will benefit from it. So do it, don't be afraid. Okay, that's the message. Thank you very much.
Thank you very much.